Alright, in this video we're going to look at evaluating several sums here. The first one we're going to look at is to evaluate the sum from k equals 1 to 100 of k. And what this means is this just means plug in 1, then plug in 2, then plug in 3, blah blah blah, all the way out to 100, and add them all up together. Well, this is an arithmetic sum, or sequence, with a first term of 1. The 100th term is 100, and to get from one term to the next, you're just adding 1, so that's your common difference. So this is definitely arithmetic. So our formula is n over 2, and then times the first term plus the nth term. So S100 is going to be equal to 100 divided by 2. Times 1 plus 100, and we did do this example in class, maybe not with the summation notation. That gave us 50/50. Okay. Well, we can actually prove by something called mathematical induction that this is in fact truth. So this is a little bit more generalized than this formula you're going to get here. This is specifically k, and then you got 1, 2, 3, 4. The sum formula over here works with any sort of arithmetic sequence. Okay, so the particular formula looks a lot like this. Well, your first term is going to be 1, and then your last term is going to be n, so you're going to have 1 plus n instead. So you got n and n plus 1. Okay, so remember this was your n, so there's your n, then your nth term, and then your first term. Okay, so this will work out exactly the same way as what we had going on before. So 100 times 101 divided by 2, that's going to be 50/50. Okay. All right. This particular formula is nice in calculus when we're doing something called Riemann sums. It allows us to write things in nice ways, and then to take something called limits. Okay. We're going to do some more examples, and then as we're going through some examples, we'll write out some more of these summation formulas. So here we have k equals 1 to 100, and we're going to do 2k. Okay, so that means plug in 1, 2, all the way up to 100, and multiply each one of those by 2, and then add them together. So we get all the even numbers, 2 to 200. This again is a arithmetic sequence. We did this one in class as well. First term is 2, last term is 200, and it was just double the last sequence we got. So 50/50 plus 50/50 is 10/100, or 10,100. Okay, there's a formula for basically the only difference between this and the others is we have this constant multiplier of 2. Now, since we're dealing with a finite sum, we can go ahead and just factor that out. So you could have this as 2 times 1 plus 2 plus all the way out to 100, and that would be the same thing. So for our finite sum that we have, we can do the same thing. Whatever that value of c is, we're just going to go ahead and pull it out of the sum and stick it out in front. Okay, and what that does for us is it allows us to recognize what we have going on, remove some of the clutter. So if we want to do that same problem before, 1 to 100 of 2k, what we can do is we can factor the 2 out first, and then go ahead and do the sum. And we'll use the sum formula we had on the last screen, which was n plus 1 over 2, and then we're just going to multiply that by 2. Okay, so we got 2, and then n is 100 divided by 2. It looks like I'm using the arithmetics, and that's the same thing. This is n plus 1. There's a divide by 2, so same thing. Okay, and there's our 10,100 again. Okay. So we're going to look at a couple more examples of this. We're going to do one where we're adding up the first 10 squares, and then something else with the first 10 squares. Then we'll also look at some cubes. Okay. So if we look at k equals 1 to n of k squared, this can also be proved by mathematical induction. This formula is a little bit more complicated. Adding up the first k squares, or n squares, would be n plus 1, 2n plus 1, all over 6. So for example, if we wanted to do the sum of k squared, so this one's not arithmetic and it's not really geometric, so we can't get away with using our arithmetic or geometric sum formulas. However, we can use this formula. So wherever you see an n over here, plug in a 10. So 10. Before I get too ahead of myself, we're writing out what that means. So we have 1 squared plus 2 squared plus all the way out to 10 squared. Then we'll plug it in with all the n's replaced with 10. So there we go. And then we'll go ahead and divide that all by 6. Okay, and we get 385. Okay, so if you went through and you added 1 plus 4 plus 9 plus 16 plus 25, 36, etc., it's going to add up to 385. Okay. So let's go ahead and mention a property. I think we did this one in class. If I add two sequences together, finite sequences, for the first n terms of two sequences, or subtract them, what I can do is I can separate them and add up all the A series and all the B series, and then do that separately, and then add or subtract them. Okay, for our finite sequences or series. Okay. Then if we look at from 1 to 10 of 2k plus k squared, we got two individual pieces. That's our A, and that's our B. So what we're going to do is we're just going to split up into 2, and because we're efficient, we're going to go ahead and factor the 2 out. Instead of writing 2k, we'll factor the 2 out. So there's the A sequence, and there is the B sequence. Okay, and this one is going to be the n plus 1 over 2, and this one will be the n plus 1, 2n plus 1. I don't think I'm going to be able to fit that, so 2n plus 1 all over 6. Okay, so those n's are going to be replaced with 10s. So let's go ahead and do that. So we have 2, and then n plus 1 over 2, or 10 plus 1 over 2, plus 10 plus 1, 2 times 10 plus 1, all over 6. Alright, now just punch this into your calculator, but don't punch it too hard. You don't want to break it. So when we do that, we get 495 as our sum of that. Okay. We're going to look at one more example, and we're going to look at adding up the sum of the first n cubes. So 1 cubed plus 2 cubed plus 3 cubed, blah, blah, blah. So let's go ahead and look at what we got going on there. Okay. So a little bit different formula. Adding up the first n cubes would be n squared, n plus 1 quantity squared. And then that's going to all be divided by 4. So if we do k equals 1 to 5, and we're going to get a little crazy here, and we're going to do 2k cubed minus 5k squared, and then plus 11, and I'm going to throw up one more formula in a minute here when we need it. So what we're going to do is, I got one sequence, here's another one, and here's a third one. So if I can split up 2, I can apply that property and split up 3. And then we got a constant of 2 and a constant of negative 5. So we're going to go ahead and factor those out. So we have 2, and then k equals 1 to 5 of k cubed. Factor out the minus 5. K equals 1 to 5 of k squared. And then the last one we have there is k equals 1 to 11. And I didn't mention this property here, but I'm going to go ahead and put it up there. So if I have k equals 1 to n of some constant c, all that means is I'm going to be adding up c n times. So for example, this one right here, k equals 1 to 5 of 11, that's just 11 plus 11 plus 11 plus 11, 1, 2, 3, 4, 5 of them, okay? That's the same thing as where it stops, the 5 or the n, times what the constant is, which is 11, okay? It's actually probably one of the easier of these formulas here. Again, where we really want to use these is in Cal 1 with something called Riemann sums, but we have everything we need to do them in pre-Cal, and it's nice to see them ahead anyways. Alright, so we got that formula up here, and let's go ahead and apply that. So we're going to have 2, and then 5 squared plus times 5 plus 1 squared divided by 4 minus 5, and then 5 times 5 plus 1, and then 2 times 5 plus 1 all over 6. So remember, you'll need to know your formulas for k squared, which was on the last example, I think, k cubed, which we have up here on the screen, and then we got the constant here, and that'll be 5 times or 11 times 5. The order doesn't matter. And when we add that all together, that's going to be 230. Okay. So the only thing that we're missing here is in calculus we'll end up be doing some infinite sums with these things, and we'll do a little bit with limits. But knowing these formulas and being able to apply them will definitely put you at advantage.